I'm going to go through this paper on energy changes. So having read the question, salts can be prepared by the reaction of acids with alkalis. So we have the general equation here, acid plus alkali will give a salt, and we need to choose the right thing here, it's water, so water would go in at this point here. This is an example of a neutralization reaction, and then we have this table. There's a little bit of an error here. This says sodium nitrate is an important salt, and this was supposed to say how do you prepare sodium nitrate, but this wasn't changed. It said how do you prepare sodium sulfate. So if we'd have read that properly, and it does say sodium sulfate, we would have needed an acid and an alkali. So the acid would have been something that would have given us a sulfate, which would have been sulfuric acid, and the alkali has to be a hydroxide or carbonate or oxide. So it would have had to be sodium oxide, sodium carbonate, or sodium hydroxide, and the only one we've got there is sodium hydroxide. However, we gave you the benefit of the doubt if you chose sodium hydroxide and nitric acid, which was this choice here. So if you'd have got either sodium hydroxide and sulfuric acid or sodium hydroxide and nitric acid, you would have got 2 marks. If you put 3 ticks in here, then you would have got 2 marks. If you'd have got the right one, then you would have lost a mark if you'd have ticked a 3rd one. Okay, so just check your marking. But it was sodium hydroxide and sulfuric acid, or sodium hydroxide and nitric acid. We gave you 2 marks if you had either of those. On question 2, again, it's helpful to read the blurb so it puts it into context. So this student is adding copper oxide to an acid, making copper sulfate. Okay, so we've got copper oxide and an acid. So it's probably going to ask us what acid it is. The student added copper oxide until no more reacted, and here we've got, we can see what it is. Complete the word equation, and there you go. It's not giving us the acid. We have to decide what the acid is. We're making a sulfate, so the acid must have been one that came from sulfuric acid. So this is sulfuric acid. Sulfuric acid. Okay, and sulfuric acid is a very strong acid. It is fully dissociated. pH 1 is what we would expect. pH 7 is neutral, and an acid is never neutral. Admittedly, this whole thing here is neutral, is a neutralization, but it did say what's the pH of the acid, and obviously 11 is an alkali. Why is the acid heated? It's to make the reaction go faster, so the reaction will go faster, or it's to completely dissolve the copper oxide. Okay, I've just checked the mark scheme, and the mark scheme says to speed up the reaction, so that's why it's heated. So that's all I've given the marks for. Okay, after the reaction is complete, some copper oxide remains. Why? It shows that you can use either the copper oxide is in excess, was one answer, so you could have got a mark for that one, or you could have got a mark for saying because it uses all the acid up, so it uses all the acid up, or another way of saying that is you could have said because it neutralized the solution, so neutralized the reaction. So you would have got 1 mark for any one of those 3. And then finally, C, the student removed the copper oxide from the solution. Suggest what the student should do to the solution to form copper sulfate crystals. So they've obviously, it says remove the copper oxide, they've obviously filtrated there. So what would they do now to get the copper sulfate crystals? Well, they would evaporate it. So they'll do an evaporation. You would have got a mark for that. You would have even got a mark for saying they did a crystallization. Okay, so you could have said they, so that there were the two techniques, but you could have said they heated it and cooled. Or you could have said they leave it to evaporate, leave to evaporate. So there was a number of ways that you could have got the marks there, but it was mainly this evaporation and crystallization. The mass of copper sulfate crystals were less than the student expected. Why was that? So some copper sulfate may have been lost during the experiment. That's a possibility. The student added too much copper oxide. It didn't matter how much copper oxide they added, that was going to be in excess. So they were only going to make it as much as they had sulfuric acid, so it was definitely not that one. The copper sulfate crystals were wet when they were weighed. Well, they would weigh heavier then. So if they were wet, they would weigh more than they should do. So the correct one is the first one. And looking at E, the question is about copper salts, and the figure shows the apparatus given to the student. There were a number of really good explanations of this plan to create the copper sulfate salt. So the first thing to do was to get some copper oxide. So you had to name the base, copper oxide, or CuO. You had to name that you were getting some sulfuric acid, so that had to be named, and you could have put the formula if you wanted to. So you had to say, so that they were the two things that were needed, and you were making copper sulfate, so that was the other named salt. It was given in the question, but you had to possibly had to name it. Okay, so the first thing that you did was added the named acid, added the sulfuric acid to the named acid to a beaker and heated. Okay, and then you took it off the heat, and then you added copper oxide to excess. So copper oxide, added copper oxide until no more would dissolve, no more dissolved. Then the third thing you did, you could have said you stirred it, which would have been absolutely fine using a stirring rod. Then you said you would filter the excess copper oxide off. So you'd filter off the copper oxide. So there's the filter bit. And then the fourth thing you would say is to evaporate the water, from the copper sulfate solution, Okay, so CuSO4 is copper sulfate, H2SO4 is sulfuric acid, CuO is copper oxide. So you'd evaporate the water from the copper sulfate solution, and that would form your crystals. Okay, so number 5, you could have also said you would leave the solution to crystallize slowly overnight. And then the safety aspect was that you would be wearing safety goggles, because it did say a safe plan, so you'd be wearing safety goggles. You would possibly say, be careful, sulfuric acid is corrosive. Sulfuric acid is corrosive, so take care not to spill. The other thing would be that you're warming the sulfuric acid, not boiling it, so warming the H2SO4, not boiling. And then you would, if you were warming the sulfuric acid, you could say you would hold the sulfuric acid beaker, with tongs. Okay, so there were a few safety aspects there. The main thing was that you got this. If you got all of this with the named equipment, the named chemicals, that would have given you 5 marks. You'd have been in level 3 and that would have been 5 marks. Naming any one of these safety requirements would have given you the extra mark. That would have given you the 6 mark question here. That you would have got the full 6 marks. Okay, so looking at question 3, we've got hydrochloric acid. It's a strong acid. We can see we've got H plus and Cl minus. Sodium hydroxide is a strong alkali. We've got Na plus and OH minus. We've got the pH of 1 and 3, and we've got the effect with universal indicator. So this is testing, do you know what makes an acid acid and what makes an alkali alkaline? So here, hydrochloric acid, what makes it acid? It's the H plus ions. They make it acid. Okay, so hydrochloric is acidic because it contains the H plus ions. Sulfuric acid contains H plus ions and sulfate ions. Nitric acid contains H plus ions and nitrate ions. So it's this that is the common ion for acids. Sodium hydroxide is alkaline, and that's because it contains the OH minus ion. Okay, so OH, you've got things like calcium hydroxide, sodium hydroxide, potassium hydroxide, so that the metal part changes, but the hydroxide part does not. So it's the OH part that makes an alkaline alkaline, an alkali alkaline. And the pH of acids is lower than it is, so the number is less than 13, so it's lower than, and that's what we were looking for. In B, ethanoic acid is a weak acid, and universal indicator can be used to show that hydrochloric is stronger than ethanoic acid, even at the same concentration. How do we know that? Most of you got this, that hydrochloric, the universal indicator will go red. Okay, so the universal indicator will go red, showing it's a pH of about 1. But with the ethanoic acid, the universal indicator will go orange, showing it's about pH 4. So you got a mark for stating the colour, and you got a mark for stating the pH. Okay, so the colour would give you 1 mark, the pH would give you the other mark. Draw a ring around the correct answer to complete the sentence. Strong acids and strong alkalis are completely ionized, completely dissociated. So all those hydrogen ions come away, or all those hydroxide ions come away. There's none left attached to the original molecule. Okay, so they are completely ionized. Okay, so let's have a look at question number 4. A student is investigating displacement reaction of metals. The student added different metals to copper sulfate solution and measured the temperature change. So what did we have? We had a test tube where we had different metals. Okay, so it had copper sulfate in, so this is copper sulfate, this is copper sulfate, this is copper sulfate, and however many copper sulfates we had. But what we put in here was metal number 1, then we put metal number 2, and this one is metal 3. Okay, so what did we change and what did we keep the same? So it says state 3 variables that the student must control. So we're looking for control variables. What did they keep the same? So when we look at this, well, we can see they changed the metal, so it wasn't the metal. The copper sulfate solution, they kept that the same. Now, quite a lot of you use the word amount. Amount is like thing, something, it, they. It really has no specific meaning. I want something more precise, so I'm looking for volume, concentration, mass, density, temperature, something I can measure. Okay, I can't measure amount because I don't know what you're talking about. So amount is a word we do not use in chemistry. It has to be volume, concentration, mass, density, temperature. It has to be a named amount. Okay, it has to be named. So quite a few of you said amount of copper sulfate, but what did you really mean? Volume. Okay, so volume of copper sulfate. We kept that the same. The other thing that we kept the same would have been the concentration of the copper sulfate. So concentration of copper sulfate. I suppose I ought to put solution at the end. Solution and solution. Okay. The other thing we could have had is the same mass of metal. So the mass of each metal. Or we could have had the same surface area. So we could have been looking at, rather than using a lump of metal, we might have used powdered metal. Okay, so we could have used the same powder grade of metal, powder grade of metal. Okay, so we've got smaller surface area. Also, some of you mentioned temperature, so the same initial temperature, the same initial temperature of the solution. And it had to be initial temperature, the start temperature. It couldn't have been anything else. Things that I had to ignore on here is the size of the tube. The same test tube, the same thermometer. That's not going to get you the marks. And it does say on the mark scheme to ignore amount of solution and amount of metal and amount of temperature. Okay, so be very specific. Okay, so this is a 3-mark question, so any one of those 3 would have got you the 3 marks. This was a really nice question because it was just a read the thermometer type question. So the temperature before adding the metal, before adding, was 20, and after adding the metal was 31, 32. It was 32, and so the change in temperature, it's 32 take away 20, which is 12. So the answer in here was 12. Okay, so we're now presented with this table of values, which is the mean temperature change in degrees C for that reaction that we've just done. And here we've got a figure, and it says draw bar charts to show the results. So not a dot to dot, but a bar chart. Okay, so we'll do that now. Okay, so here is the bar chart. Quite a lot of you made a mistake with the cobalt. It was 4.5, and quite a lot of you put 4.5 up here, which is 5. So 4.5, if we count what these squares are, each small square is worth 0.2. So 0.2, 0.4, and then half a square is 5. And I have to mark this to plus or minus half a small square. So half a small square. So if you're more than half a small square out, you don't get the mark. So you've got 2 marks for plotting the graph correctly, and then you've got 1 mark for labelling it. And again, quite a few of you labelled cobalt here at this point and gold here at this point, and it needs to be in the middle. So it needs to be underneath the bar itself. Some of you actually labelled it like this, and that was okay. Okay, and magnesium you put on here, that was okay. So I gave you those, but if you put the label on the wrong part, so if you put it here or here, you didn't get the mark. It had to be in the middle of the bar. Okay, so that I knew where it was. Then it says, why is the line graph not suitable? These are not continuous variables. They don't vary like a number varies. So these are categoric or not continuous. So that we can say they're not continuous variables. Not continuous, they're not continuous variables. Or you could have said that they are categoric. They're in categories. They are categoric variables. And I don't think anybody really got that. Maybe 1 or 2 people, but the majority of people didn't get that, but that's what it is. Okay, so use the results to work out which is the most reactive. So if we have a look, we can see, even from here, that magnesium is the most reactive. We know it's the most reactive. We've got, please stop lying calling me a careless zebra. We can do that. We know what the reactivity series is. We know magnesium is very reactive, but we'll get a mark for saying magnesium, but we need to say why. It's not because it's at the top of the reactivity series, which we know it is. It's because it's got the greatest temperature change. So the reason is the biggest temperature change. The biggest temperature change of all. Okay, so that would get us the mark. Here, explain why there was no temperature change when silver metal was added to the copper sulfate solution. Majority of you got that. You said that silver was, I think quite a lot of you said silver was an unreactive metal. It's not that silver is unreactive, it's just that silver is not a reactive metal in this situation because it's below copper in the reactivity series. So we can say silver doesn't react. So we get no temperature change because silver does not react. Why doesn't it react? Because silver is below copper in the reactivity series. Silver is below copper in the reactivity series. Okay, and that's the answers to those.